My screen is visible. Say yes or no.
Yes, sir.
Okay. Okay. Let's start. So tell me, is my voice is audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay. So in the previous lecture, we saw the number system with base 10 for decimal, for hexadecimal, for octal, and other also like base 5 also we saw, right? Now, one more topic is there with ones complement and twos complement. Ones complement and twos complement. We also have nines complement. Similarly, this is in the binary number system. This is for the binary number system, and a nines complement and the tens complement similar, same for the decimal number system. Okay, so what is the meaning of this nines complement? For example, if any number is decimal like 8, 5, 6, for example, like that. So for the similar, for the same number of nines, right? You have to subtract this number like 999 and subtract this number 856. Okay, that means, as you know, in the decimal number system, the numbers are from 0 to 9. The largest number is 9, so we have to subtract the numbers and bits by the maximum number, that is 9. Okay, so we are subtracting our number 999 by this, right? Like this. So what you will get? 9 minus 6. What you will get here? 3. After this, tell me. Anyone?
4,
4,
1.
1. So this will be your ninth complement. Okay. Similarly, if I ask you to find out the tenth complement, so what you have to do? Add plus 1 in ninth complement. First, you find out ninth complement of any number and then add 1. So that will give you tenth complement. And just like you will get 144 will be the tenth complement. Understand? Same process we have here in the binary number system also. For example, you
Sir?
have any, yes,
Sorry, 143 will be the 9th complement of like specifically 856, right?
for 856, yes.
Okay.
Now you have any number. For example, I am taking 1101. For example, this is my number, and they said find out the ones complement. As I told you, in the binary number system, the number is only 0 and 1. That means you have to subtract from 1 all. That means you have to subtract from 1, 1, 1, 1. All ones you have to take. Okay. And then subtract your number here like 1, 1, 0, 1. Subtract 1, 1, 0, 1 minus 0, 1, 1, 1, 0, 0. Like that. So this will be what? Ones complement. Similarly, if
So,
I ask, yes,
so, so even if it's five number, then we also have to take 5 times 1.
see, what, yes, yes. If number, I will give you other example also, okay? So this is one's complement, understand? If you want two's complement, what you have to do? Plus 1. So it will give you 0, 0, 1, 1, right? Same. For example, I am giving you another example. Suppose you have 1, 0, 1, 1, 1, 0, 1, like this, okay? Any number, I am giving you any number. And I'm asking to find out the ones complement. So what you will do? Take all ones, similar number of digits. 1, 1, 1, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7. So I have taken 7 ones, right? Now you subtract your number. That is 1, 0, 1, 1, 1, 0, 1. So it will give you 0 here, 1 here, 0, 0, 0, 1, 0, like this, right? This is your ones complement. Now, if I ask you find out two's complement, so what you have to do? Plus 1. In one's complement, plus 1 will give you two's complement. So what you will get here? 1, 1, 0, 0, 0, 1, 0. Right? That is the way of finding the ones and twos complement. Now, question arises, if you have any number and you want to add it, okay, how I will add? See, you have to add the 2 bits only. For example, you have 2 bits. 2 bits. Like I'm saying that as I'm taking only 2 bits. Okay. So possible combination not 4. Either if A and B we are adding it, right? So it is possible that both are 0. 1, 0, another 1, 1, 0, 1, 1. Right? And if you add two numbers, just like I'm adding in the decimal number system like 56 and suppose 14. So I'm adding this one. So 6 plus 4 is 10. I'm taking 0 here and 1 is the carry. Same thing. This is called as the sum and this is called as the carry. Right? Similarly here when you add A plus B, I'm adding it. Okay, I'm adding it. So what you will get? 0 plus 0 will give you sum and carry as two outputs. So I'm just making here two columns. One is for the sum, another one is for carry. If you add 0 plus 0, it will give you sum as 0, carry as also 0. If you add 0 and 1, if you are adding 0 plus 1, what you will get? 1 and without any carry. You will not get any carry. So sum in 1, carry is 0. If you again add 1 plus 0, same 1 and 0 you will get. Now if you add 1 plus 1, what it will give you? Actually 2 way it will give, right? But in the binary number system, 2 means 1, 0, right? So here you will get 1, 0. That means sum is 0 and carry is 1. So you will get sum as 0 and carry is 1. So this is the way of adding 2 bits. So that's the way. Now, for example, if you have any example, I'm saying they are saying add 4.
So can you show that table?
Yes, yes. This is only when we have 2 bits, right? Now, for example, you have two numbers, like they said, add 4 and 5. They said, but in the by using the binary addition, by using the binary addition, you add 4 plus 5. So what is the procedure actually? They said, first convert into the binary form. That means this is in the decimal number system, right? You have to convert into the binary form. I know you can do it. I'm directly writing. 4 you can write down as 100, right? In the binary form. Plus, you can also write down 5 as in 101 in the binary form. So we need to add it, right? So how you can add 1 as you are adding in the decimal number, same thing you have to do here. You have to take 100, that is your A. B is your 101, right? Now you see by this table, I have to add respective digits 0 plus 0, 0 plus 1. It will give 1 as sum. You can see here. If you add 0 plus 1, it will give sum as 1, carry as 0. So it's 0 plus 1 will give you 0 carry, right? 0 plus 0 again 0, 0, 0, all zeros. Again carry is 0. If you add this 1, 1 plus 1 will give you 2. And 2 means what? 1, 0. That means sum is 0 and carry is 1. So sum is 0 and carry is 1. So the total number you can see it is 9. Okay, so this is the simple example I gave you for adding two numbers in a binary addition form. Okay, binary addition. Don't forget, if binary addition is written, you have to do in the binary form, not directly you write down 9. No, you have to go with a binary form. That means convert into the binary number, then add it and tell me the answer like that, right? So that is the way of adding the two numbers. Now you see,
Sir,
we have
once
a
can you
next.
show the table, sir, the binary addition?
Yes, yes. 0
Yeah,
plus 0
thank you.
will. Okay. So the next topic that we have is logic gates, which is very important. Logic gates. Logic gate is what? It is a physical device which performs the logic operation on one or more logical input and produce a single logical output. Okay. You can assume it's just a box where we can provide so many numbers of input and it will provide the logical single output. Okay. This is it is a physical device. There are three types of logic gates. One is basic gates. Second one is called as universal gate. And third one is called as the arithmetic gates. So in the basic gate, we have AND gate, OR gate, and NOT gate. In the universal gate, we have NAND gate, NOR gate. In the arithmetic gates, we have XOR gate. Sometimes it's also written as same XOR. It's also written as XOR. Okay, both are same thing, same. And similarly, XNOR or XNOR. Both are same thing. Okay, these two are both are same. Okay, so let's start with the basic gates. So here we have an AND gate. Okay, so AND gate symbol that we are using is like this one. AND gate symbol that we will use is this one. And if now the second thing, if suppose I'm asking to write down about the AND gate. So first thing is its symbol. Okay, second thing is its truth table. Okay, what's the meaning of truth table? Truth table tell us the combination of input and output. For example, you are taking A and B are the inputs. Okay, so here I am assuming A and B are our input, and I am saying Y is our output. Yes.
So what are for the arithmetic gates?
Arithmetic is XOR gate and XNOR gate. We will go in detail about it. Okay. So in the logic gates, we have three parts. First is basic gates. I started with AND gate. Okay. So AND gate symbol is this one, and representation is A dot B. A dot B is the representation of AND gate. Now I am saying the truth table means describing the relation of input and output. For example, you have A and B as an input and Y is your output. And as I told you, the representation is A dot B. Okay. As I have taken two inputs, the possible combination is 4, 0, 0, 0, 1, 1, 0, and 1, 1. Right? In the AND gate, it will be 1 only if all the inputs. In the case of AND gate, the output will be 1 only if all the inputs are 1. All the inputs are high or 1. High or 1. Okay. So in that case, all other will be 0 only if, as you can see, inputs, both the inputs are 1, 1. That's why we are getting output 1. If you are having, suppose 3 input, A, B, C, D, anything. So even in this case also, output will be 1, that is A dot B dot C dot D, like this, right? If you are having all ones, then only it will be 1. Otherwise, if any of the input is 0, for example, this is 0, in that case, it will give you 0 only. So in the AND gate, output is 1 only if all the inputs are high or 1. Okay. Now we will have a second type of gates, second type of basic gate, that is OR gate. Representation is like this, where we can have so many inputs. I am starting with A and B, and the output Y is written as A plus B. Okay. And the truth table, which is again important part. In the case of OR gate, if you are having the inputs A and B, Y will be equals to A plus B, like this. And as I told you, we have two inputs. So the possible combination are 4 only, 0, 1, 0, 1, like this. Okay. In case of OR gate, the output is 0 only if all the only if all the inputs are 0. All the inputs are 0 or no. So other than that, if any of the input is 1 or all the inputs are 1, you will get 1, 1, 1 as an output. Now the third basic gate is the NOT gate. Here in the NOT gate, the representation or the symbol that we are using is like this one. Sometimes it's also representing like this one. Both are the same thing. Okay. You can make either this symbol or you can make either this symbol. But very important point is here we have only a single input, that is A. Okay. In the NOT gate, we have a single input, that is A. So if I draw, this is our input and this is Y. As there are single input, there is possibility of only 0 or 1. Y is represented as A bar. Okay. A bar, thus complement or inversion. Complement or inversion. So here it is A bar. So what you will get? 1 and 0. Just opposite of that. Now, so we have seen about the basic gates. Basic gates are AND, OR, and NOT. Now we have a universal gate. Why? What is the meaning of this basic gate? See, with the help of these basic gates, you can design any circuit by using basic gates. That means combining AND, OR, and NOT. We can design any gate. We can design any gate, any function or logic. Now, the second part of the logic gate is universal gate. Universal gate. With the help of universal, first, there are two types of universal gate. One is the NAND gate. Another one is NOR gate. By using these universal gate, that means by using a single means either of this gate, either you use NAND gate, either you use NOR gate. By using a universal single type of type of universal gate we can design any function. First, I am starting with a NAND gate. Okay, so the NAND gate representation is like this one, and is like this one, right? If you remember, AND gate is like this one, right? And if you can add one not here, this is NAND gate. Okay, so A, B. I'm giving A and B as input, and as an output, you will get A dot B was AND. Complement of AND operation is your NAND gate. That means first you find out A dot B, and if you take the complement of it, just opposite, complement is just opposite of it. Okay, so you will get the NAND gate output. So if you have 0, 0, 1, 1, as I am taking two inputs, 0, 1, 0, 1. So if you take the AND operation, as I told you, it is one only if all the inputs are 1. So you will get 1 and all zeros. Now you have to take the complement of this function, that is your y, that is your output. Okay, so if you take the complement, 0 will be 1, 1 will be 0 will be 1, 0 will be 1, and 1 will be 0. So you can say is 0 only if all the inputs are 1. This is the logic of NAND gate. Now I'm also saying about the NOR gate, how we can design this NOR gate. Okay, so in the NOR gate, we have a logic like this. Okay, and this is the way of representing. If you have A and B, and output will be A plus B 4 bar. Okay, and as I have taken two inputs, you can design a truth table like this: y is equals to A plus B. This is the first part, that is OR gate. Okay, and if you take the complement, that means A plus B whole bar, that is your NOR logic, right? So as already we know this combination, right? So you can write down as this is OR gate. OR gate gives only 0 if all the inputs are 0. Otherwise, it will give 1. Just complement, just opposite if you take, this will be 1, 0, 0, and 0. This is your NOR gate logic. Okay. In the starting, I told you, you can design any circuit by using the universal gate. So how we will design it? For example, you have any function. First, I'm writing a simple function like a b dot b plus c dot d. If anything is not there, you can assume a b plus c d. Both are same thing. Okay, dot is not given. That means it's dot only, right? Even if dot is not provided in between, it's a b plus c d. Okay, that means they are saying here we have an AND operation, and here we have an AND operation. And in between them, we have a OR operation. This is OR operation. And they are saying by using the logic gate, you design this function. Okay, how we will design it? You see, I can take one AND gate here like this. For this, I am saying, okay, for A dot B, you can take A here, B here. Here, what you will get? A dot B. Now you have CD. You can design it by the AND gate like this. So this is your C, your D, and you can design C dot D. Now in between them you have OR gate, right? So if I give to the OR gate like this, what you will get? A dot B plus C D. Okay, so this is the simple way of representing by using the basic gates. As I told you, you can design any circuit by using the basic gates. And you can see this is what a sum of product. Sum of product. Why it's sum of product? This is a product, right? A dot B is a product. C plus D is a product, and sum of in between them we have a sum. So any function is in this sum of product form. You initially use and then you use OR, because we are first having the product and then we having the OR gate. So by this method, you can design by using the basic gate. Now, after that, we saw universal gates, right? Universal gates. That says by using either of the universal gate, means by using AND gate logic, you can design this circuit. But how? So I'm changing the color and telling you the procedure. Okay. What is the first step? Design any circuit. Design any circuit by using basic gates, as I did for this one. After that, bubble the circuit. Bubble the circuit. What is the way? What is the meaning of this bubbling? You see, I have taken AB plus CD. Okay, I already made this circuit. I'm just redesigning this one. Same. So I gave AB for AND gate. This is A and this is B, and I was getting A dot B here. And then I gave here that is CD, and I was getting CD here. And after that I gave to the OR gate logic, right? If you remember. And here I was getting A dot B plus CD. This is the implementation by using the basic gates. Now, what is the question? How we can design by using the universal gate, that is NAND gate. So what you can do? You bubble both sides. One bubble here. I'm just changing the color so it will be visible. You bubble here, bubble here. One complement, two complement. It will not affect your output, right? One bubble here, one bubble here. So now you can see this is what a NAND gate, right? This is also a NAND gate. And always remember the bubble, this is bubbled OR gate. This is called as bubbled OR gate. Bubbled OR gate is equivalent to NAND gate. Both are same thing. Either it's the bubbled OR gate or NAND gate. So what we can do after this? You can again design this one like this. Both are same thing, right? A, B. Again, here we was having the A, C, and D. After that, this bubbled OR gate is equivalent to NAND gate. So I can also draw one NAND gate here and then combine the inputs. So this is A dot B plus CD. Okay, so this is the way of finding or designing any circuit by using the universal gate. Now, question is what? For example, again, I am giving you one example like A plus CD. This is my question. Okay, I'm saying design by using basic gate. That is the first thing. So what I will do? First, you have to see the product, sum of product. For NAND gate, I'm talking. I'm talking about the NAND gate only. I'm not talking about NOR gate. I'm talking about the NAND gate. Okay. So first you have to check whether it's in the sum of product form or not. Yes, in the sum of product. We have a product and then we have a sum. Right. After that, what you have to do? You have to take A directly. Here we have AND operation between C and D. So what I will do? I will make one AND gate here. Will take here like C and D. Okay. So this will give you what? C dot D. And we also require one OR gate. So I can make one OR gate here. You will get A plus CD. Now, as I told you, you have to bubble it, right? With different color, I will show you. Bubbling. So what I will do, I will make one bubble here, one bubble here. Again, I want one bubble here and one bubble here. So this is what a bubbled OR gate, right? And the bubbled OR gate is equivalent to a NAND gate. You can see this is also a NAND gate. The problem here is this is only a NOT gate. Okay, this is only a complement. So now for this, we have one procedure how to design NOT gate using NAND. How? See, you can take one NAND gate like this. If you combine both the inputs like this, and you are providing A, it will behave. This is NAND gate, okay? So this is NAND gate. If you are providing A here, you will get A bar. Okay, so if you want a complement or you want to design a NOT gate, you combine both the inputs of NAND gate, you will get A bar. So you can do one thing here. I'm just drawing the same thing. You combine both the in terminals and make a NOT gate here. And the bubbled OR gate, as I told you, it's a NAND gate only. And here we was having the NAND gate already. So it's A, C, D, and you can provide it here. You will get what? A plus CD. So the procedure is what? You have to design by using the basic gates, bubbled it. After bubbling, you have to check if any single NOT is there, then you can represent by combining the terminals that will behave as a NOT gate. Okay, and then bubbled OR gate you can represent by a NAND gate, right? Now, the next term that is important, how to design a AND gate. AND gate using NAND gate. That means I have a NAND gate. How I can design a AND gate? So I have a NAND gate like this. This is A, B. So what it will give A dot B whole bar. This is the NAND gate, right? I want to design a AND gate. So what I will do? I have to take the bar or complement. So you can get AB. So what I will do? I will combine these two terminals or not. As I told you, if you combine the terminal, you will get a NOT operation and you will get AB here. Okay. So like that you can do for the NAND gate logic implementation. Now, if, for example, you have A plus B and C plus B. For example, like this, we have any function. I gave you any function and I said you to represent by using the NAND gate logic. Represent using the NAND gate logic. So what is the procedure? You see, you can check. This is what sum, this is sum, and so this is sum and this is sum and this is product. This is not a SOP, sum of product. No, this is not a sum of product. This is product of sum. Okay, that means product of sum. This is sum and we are taking the product. So it's product of sum. So in such condition, you multiply it, means open these brackets, A dot C, right? You know the how to open brackets, A, C plus, again you multiply A plus CD. So it's AD plus BC plus BD. Okay, now this is in the sum of product form, SOP form. Now you know this is AND operation, this is AND operation, this is AND operation, this is AND operation. After that we have OR operation. Just in 2 minutes I'm designing this one. This is AC, right? AC. So you can write down this is AC. After that you can write down like AD. This is AD. This is BC. So you will get BC here. And then similarly you will get here BD. Okay. And one OR gate I require. So OR gate you can design like this. And that will give you an output of sum of all, right? And if you want to design by using the NAND gate, what we can do next? Bubbling. One bubble here, 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 one bubble here. You can see all are NAND gate now. These are all NAND gates, 1, 2, 3, 4, and this is bubbled OR gate, and this bubbled OR gate also equivalent to a NAND gate, right? So now in this manner you can design by using the NAND gate. Understand? This is the procedure. Now I'm showing for the NOR gate also. How we have seen for the NAND gate. Now how we can represent by NOR gate. For the NOR
sorry.
gate, yes.
So NAND gates only work on the sum of product
Yes.
logic.
So
You
yes,
can't do it with anything else.
Yes, you can. You have to convert into SOP form, sum of product
Okay.
form. Okay.
Okay.
By multiplying, you will get it. Now the
Yes, sir.
NOR gate logic says if you have in the product of some form, like this one, this is in the product of some form, right? So what you have to do, same as you have done, you have to first represent by OR logic, right? See, this is by basic gates. This is A and B, A, B. So what you will get? A plus B. I'm using OR gate here. Similarly, you also do one thing here, like it's C and D. So what you will get? C plus D. After that, I want one AND gate logic. If you can see, it's dot, right? So you have to make one AND gate here. Now, as we have done in the NAND gate, you have to make the bubbles. One bubble here, one bubble here, one bubble here, one bubble. Complement. Here one bubble, here one bubble, here one bubble, here one bubble, right? So you can see this is NOR gate, NOR. This is also NOR. And this is bubbled AND gate. Bubbled AND gate is equivalent to bubbled AND is equivalent to or NOR. Okay. So this is again you can draw like this. So this is a NOR logic. Okay, fine. So this is the way of representing. For example, if you have any function which is in the POS form and SOP form, how you can convert into POS and SOP, right? So that is the next thing that is important for us. For example, you have any function like A plus C D like that. Okay, so this is, you can say it's a SOP form or some of product of some form. Tell me.
SOP, sir.
SOP.
It's SOP form. How to this is SOP, right? How to convert into the POS? So it's a absorption method by which you can. This is similar to A plus C and A plus D. Okay, that means A plus C first time and A plus D. So by this you can convert into the POS form. One more example I'm giving you. Suppose you have any function A plus B bar C D like this. Okay, and this is in the SOP form. So what I can do, I can convert into the POS form, because if I have to design by using NOR gate, I require POS form of it. So it will be what? A plus B bar, then A plus C D. Again, this is A plus B bar. Okay, and for this also you can open it, right? So it will be A plus C and A plus D. Now you can see this is in the POS form. So like that, if any function is there, first check whether it's in the SOP form or POS form. If it is in the SOP form, you can directly go for the NAND gate representation. If it is in the POS form, you can go with the NOR gate of implementation. If any of it not there, then you convert into it, right? For example, any function is there, like you have A plus B and you have C plus D like that. What you have to do, this is in the POS form, product of sum. And you need to convert into SOP for NAND gate representation. You just open it. It will give A, C plus A, D plus B, C plus BD like that. Okay, so it's up to you which type of implementation we actually require. Okay, now the next topic that we have, any function is given to us like this. Any function, first I'm giving you some basic theorem in the algebra. Okay, they follow some properties actually. So in the case of Boolean algebra, we have some basic properties. By using these properties, we can simplify any expression. Okay, suppose first one is associative property. Associative property. Associative property says that if you have suppose A dot X dot Y dot Z and operation. Okay, if any function is for AND operation for 3, so you can do one thing. A dot X you do first and then with Z later, which will be equals to X dot Y dot Z. That means you first take the AND operation between Y and Z and later you do AND operation with Y, X. Both will be same. Okay, that means it follows the associative property. Second, it also follows the commutative property. Commutative property says that if you have any function like X dot Y, it is also equal to Y dot X. This is the commutative property. Okay, and there are some distributive properties are also there. Third one is distributive property. They said that if you have any function like X dot Y, for example, X plus like X plus Y Z. So you can write down as X plus Y, X plus Z. Like that also you can write down. Okay. So this is called as the distributive property, and the same is similar we have seen here also. That was also a distributive property only. And for example, if you have function like X, Y plus Z, then also we can write down as X, Y plus XZ. Right? So this is the distributive property. There are some basic theorems. Okay. So I'm writing about the basic theorem, and by using these basic theorem, we can simplify the expression. Okay. So the basic theorems first says X plus 0 is equals to X. X dot 1 is equals to X. X plus X bar is equals to 1. X dot X bar is equals to 0. X plus X is equals to X. X dot X is equals to X. X plus 1 is equals to 1. X dot 0 is equals to 0. Okay. If you take the 2 times complement, it will give you X only. We also saw the commutative property. Same thing I'm writing here. So it will make one table. Commutative. Commutative says X plus Y is equals to Y plus X, or X dot Y is equals to Y dot X. Associative, we saw already. I'm just writing here. Associative says X plus Y plus Z equals to X plus Y in bracket plus Z. If you have X, Y, Z, either you take dot operation between them earlier, or you can make it like this. Now we have a distributive also. Distributive property says X, Y plus Z is equals to X, Y. That we already seen. I'm just making one table, so it will be easier to understand. X plus YZ will be equals to X plus Y and X plus Z. We already written these things. Now the De Morgan's theorem, which is important. De Morgan's theorem says X plus Y the whole bar is equals to X bar dot Y bar. That means complement of each literal and also the change in operator. Okay, I will explain in detail after this. Change in operator and complement of each literal. Complement of each literal. That means I am taking the complement of each literal. That means X plus Y was there. So I taken X bar, Y bar. And change in the operator, that means it was plus, so now it will be dot. Same thing here, X, Y bar will be equals to X bar plus Y bar. And the last theorem that we have is the absorption theorem. It says X plus XY is equals to X, and similarly X plus Y is equals to X. Okay, Now you can ask me how it is possible actually, right? So you can do one thing to understand absorption theorem. You can take x plus xy. So what I can do, I can take x common. It will be 1 plus y. Now you come here and see 1 plus x or n 1 plus y is equals to 1, right? So here 1 plus y will be equals to 1 and x dot 1 will be equals to x. So by this method, you can prove also how it's coming, right? So we have written all the theorems which is required for us. Now I am giving you a simple example how the question will come in your exam, right? So by using these theorem, how we can solve the problem. For example, I am saying first question x bar plus y. So what is the first step? You open it, right? So you can open, so you will get x bar plus xy.
You finish the De Morgan theorem.
Yes, De Morgan's I will come. I'm just giving a simple example, and after that I will explain De Morgan's theorem. So here, if you open this one, you will get x bar plus xy. Now you come here and see x bar is 0, right? So if it is 0, so it will be 0 plus xy, and that will be xy. That is your answer. Now, what is De Morgan's theorem? Okay, De Morgan's so says that De Morgan's or complement, both are same thing. Okay, complement. If any function is given to us like f, this says x bar y z bar plus x bar y bar z. Okay, like that they have given. So the first step you can do is duality. Duality. What is the meaning of this duality? That means changing in the operator, change of operator. That means if you have a plus or operation, you change it with the dot operation. If it's a dot operation, change with the plus operation. It's called as duality. So in the same function, this is actually a dot, as I told you. Even if it's not there, you have to assume as a dot. Okay, so I can write down as x bar plus, because dot, right? So it will convert to positive plus y plus z bar. Now this is plus, so it will become dot x bar plus y bar plus z. Understand? After that, this is the duality. Now the second step, this is step 1. This is step 2. So in the step 2, what you have to do? Change of, or not change, complement of each literal. Complement of each literal. Literal means what? X, Y, Z are your literals. Complement, that means, for example, X bar is there, right? So you have to take one extra complement here, plus Y complement, plus Z complement. That means complement of each literal that you have to do. Same thing here, X double bar plus Y double bar plus Z bar. Double bar is similar to normal function, right? So it will be X plus Y bar plus Z. 2 times complement will give you the same function, right? Or same literal. So it will be x plus y plus z bar. So De Morgan's or complement, if any function is given to you and they said that find out a complement of this function, or they say apply the De Morgan's theorem, that means they are asking to find out f bar. Okay, and f bar can be find out by 2 steps. One is duality, another one is by complement of each literal. The second thing also, you can find out the same function f. For example, if I was having this function x bar, y, z bar. Okay, I'm just taking any other example, x bar, y plus, suppose z. Okay, xz, like this. Okay, so what I can do here, yz you take, otherwise it will be, okay. So we have one function like this. I'm saying find out the complement of the function. I'm saying find out f bar. So what you will do, take the dual of the function. Dual means what? Changing in the operators. So it will be x bar plus y dot y plus z, right? Now you have to complement each literal, complement of each literal. So it will give you x double bar plus y bar dot y bar plus z bar. And double bar will be equals to a single bar. So x plus y bar plus z is your answer. This is the simple way by you applying the duality and the complement of each literal. Also, you can do one thing. You can apply f bar, and that is x bar y plus y z. The whole bar, right? So now if you open the whole bar, what it will do? It will convert that you have seen earlier also in your 12th. It will change the operator like this, and yz whole bar will come, right? If again you open this one, it will be x double bar plus y bar. Similarly, this will be y bar plus z bar, because De Morgan's theorem says that x plus y whole bar will be equals to x bar dot y bar, and it also says that x y whole bar is equals to x bar plus y bar, right? So if you do like that also, you will get the same answer as we have written earlier. Okay, so either you can go with this process, or either you can apply duality and the complement of each vector. Okay, you can also go for the simplification by using these methods. Okay, we have so many steps. Like here we have one example for the simplification. I am saying a b bar plus a b c plus a c bar d. Okay, so what we can do here, you can take a common. I'm talking about simplification. That means you have simplification. You have so many literals like this, and we have to simplify the expression by using the theorems. Okay, so you can take as b bar plus bc plus c bar d, right? You can also go with a, and this is what absorption method also we can apply, or distributive property. So it will be b bar plus b and b bar plus c bar d. As we know, this b bar plus b will be equals to 1. So it will be a b bar plus c bar d. Now again, you can do this theorem, apply theorem here. So it will be a b bar plus, if you open this one, what you will get? C plus c bar and c plus d. Again, this c plus c bar will be 1. So it will be a b bar plus c plus d. Like that also you can solve. Okay, so please solve some question based on the simplification. I will give you a digital assignment in your module today, so that you solve. Okay, that you also solve and submit before the time. That's all from for the today's lecture, and we have already seen some part of it. I'm just explaining what we actually saw. Number system, we complete number system and conversion of bases we have seen in the previous lecture. Today we saw the Boolean algebra, logic gates, concept of universal gates, simplification and implementation of Boolean function. We will solve some more questions based on implementation and simplification of Boolean function. And also I will give some question in your digital assignment, so that you have to complete before exam. Okay, it is the first thing. And we already covered the BJT and this concept of MOSFET. Only the small part is there, that is amplifier. It's also similar to BJT and MOSFET. All are same circuit. Only some specific circuit which is used for amplifier, we will solve some numericals based on it, and then we will have a oscillators. So that we will cover in the next lecture. So in for your exam, you have module 5 up to module 5.
So will
Excuse
we
me,
get theory
sir.
questions?
Yes,
So can you assign the DA submission date after CAT 2?
I can give you, but it's better if you solve earlier, right? Because before exam, if you solve, it will give you idea about the exam.
All right, sir.
So will we get theory questions?
No, mostly numericals. Small question, conceptual question I can ask, but it mostly numerical.
Okay.
Sir, how much weightage will each module have? Like 3, 4, and 5? Will it be 10, 10, 10 or?
So 1 minute, huh? Just okay. So okay, I will tell you in the next lecture. Here
Okay, sir.
that guideline is not here.
Okay, sir.
Okay, so I will take the attendance directly from here. Thank you. Thank you so much.
Thank you so
Okay,
much.
sir.
Thank you, sir.
Thank you.
Sir, can you post today's note?
Yes, yes, sir. So I am uploading the today's notes. You can download from here.
Sir,
Thank you.
sir.
Thank you.
So can you give some extra
you, sir.
problems like apart from the A1
Yes.
for us to
Yes.
practice?
Yes, yes. I will give you in the DA assignments. So there you can solve also.
No, sir, apart from the A, some extra questions.
Extra
from-
question you can solve from the book. So I will give you the name of that book.
Okay, sir. Thank you.